Okay, so let's talk about some lungs. So here we go, here's our lung. Gosh, there's trash too. Let's talk about some lungs. All right, this one sounds good. Yeah, there we go. Okay, here's our lung. Not a very good picture, but within the lung you'll see these branches here, and it will branch a lot. Something like a fractal, right? And say we're branching. There's these cartilage rings to support the bronchi, is what they're called, the bronchi. As we go in this lung here, what you'll see is that at the end of these branches are alveoli, where gas exchange takes place. There's a capillary bed right here. And this membrane here, there's a little membrane right here surrounding the lung. There's a little space, it's a very small space. It's called the pleural space. And you got the visceral pleura and the parietal pleura, where it occurs, as the two borders between it. And so we'll get gas exchange here. And now we're going to talk about negative pressure ventilation. So I'm going to go grab an eraser here and show you how that works. So, wrong way. All right. Yeah. Okay, so I'm going to draw a little bit more simply. Do you remember that law that states that as volume increases, pressure has to decrease as well? Well, that plays a huge part in the lungs. So here's our lung. What am I drawing there? So when we inhale, we have our diaphragm right here. When we inhale, the diaphragm constricts and it will go down like this, right? It'll go down. And what happens when that happens? Air from our outside will come rushing in. Why? Because we're increasing volume, pressure must increase. And so the pressure inside here, we have this pleural space as well, is less, so it's like -2. It's less than the 0 of atmospheric pressure. What happens is as our lungs will expand, then, there's also like these elastin proteins that want to make the lung collapse, right? Kind of compress the lung. What will happen then is we'll compress, and then pressure in here will get greater. And then we exhale, and basically what that does is this pressure then, it's like -8, will then cause the lung to collapse, but not entirely because of the pressure in here. And then we'll expel our CO2. So that's more or less how we inspire and exhale. So, let's see this. Okay. There's two things when it comes to lungs. We have compliance and elastance. So here's pressure, here's volume. Here's like the normal pressure volume cycle for like a normal lung. And here are lungs that are that have issues with them. Actually, sorry. It's pressure, volume. Okay. So elastance equals change in pressure over change in volume. Compliance equals change in volume over change in pressure. What this is saying, elastance, is like stiffness. And this is compliance. So what this is saying here is that basically to get a volume change, our pressure has to go way up. So this would be elastance, because look how much pressure we have to exert, and we only get a certain amount of volume. This is obstructive. It's like COPD. And this compliance here, this is restrictive. No, sorry. What am I saying? This is restrictive. And this is obstructive. Basically what these are saying is, if I have an elastic lung, for me to breathe in, it takes a lot more pressure. I have to exert a lot more effort. That's why it's called restrictive. You have a hard time breathing in. When it's compliant, you get a huge volume change with not a lot of pressure. And so I can breathe in really easily. It's easy. But I can't really breathe out. It's a lot harder. That's why it's called obstructive. It's hard to breathe out, because my volume is so huge. This is an example of an elastic lung. This is an example of a compliant lung. And that's a normal one. So that's how elastance and compliance can affect your lungs. There's also another thing here, and that affects pressure primarily, and it's called Laplace's law. We're going to talk about it right now. Okay, Laplace's law basically says that pressure equals 2T over R. R being the radius, T being the water tension, and P being pressure. Now within our lungs here, there are waters. I'm just going to draw them as H2Os. H2Os all around here, right? And you know what H2Os like to do, right? They like to hydrogen bond with each other. So oxygen will be bonded with it. And so they form this nice little mesh of hydrogen bonds around the lung. And it's good because it helps keep our compliance down within normal levels. But at the same time, we don't want too much water tension because that increases pressure and that will cause restrictive airflow. It'll be harder to expand the lungs because of these waters causing surface tension. So what our body does to mitigate this is we have pneumocytes type 2. We have type 2 pneumocytes. And what those do is they release surfactant. It's a polar head with a fatty tail. It's like a phospholipid, but it only has one tail instead of two tails. And what they'll do is they'll just kind of sit between these waters. And draw them like this. They'll kind of sit between these waters, and they'll decrease surface tension, decreasing pressure, decreasing elastance. And one thing that these pneumocytes will respond to is cortisol. High stress. They have cortisol receptors. So cortisol will increase surfactant, decreasing pressure, and thus making our lungs more compliant. So that's all I have really on surfactant and compliance, elastance, and lungs and how we exhale and inhale. Okay, one thing I forgot to include was a pneumothorax. Basically what that is you have your lung here, right? You get your pleural space. What it is just a hole in the lung. And what happens when we got a hole in the lung? Well, this space fills with air and then basically becomes the same pressure as the outside. And it was what was keeping the lung from collapsing. And now, no matter what, these elastins, everything will work together just to collapse the lung, and you'll get a collapse like this, and the lung will shrivel up into a ball, and that lung is useless. So that is the pneumothorax. You get a hole in your lung. Okay. All right. Now we're going to talk about the alveolar gas equation. Come on. There we go. Okay. Alveolar gas equation means PaO2 equals FiO2 times atmospheric pressure minus pressure due to water in the lungs minus pressure, arterial pressure of like CO2 over R. And then I want to find our PO2 we get. Yeah. Okay. All right, what is this big old mouthful of things? Okay. Well, I'll show you. Here's an alveolus. Here's oxygen. Oxygen, we know it accounts for like 21% of atmospheric pressure. Well, that's about like 158 millimeters of mercury. And that makes it 21%. What we're trying to figure out, because clinically this is important, what is the partial pressure of oxygen in here? Because what it will be in there is very close to what it will be in the arteries. So, that's why we want to figure this out. So, FiO2, normally it's like 0.21. That stands for 21%. But patients could be on supplemental oxygen, increasing this to 30%, 40%, or even 60%, depending on the mixture that a physician has them on. But for a normal healthy person breathing atmospheric oxygen, it will be 0.21%. And that's regardless of where you go in elevation. Atmospheric pressure at sea level is 760 millimeters of mercury. And within our alveoli, right, there's water. It's very moist and humid in there. And so there's a pressure coming, gas pressure coming from water vapor. And so that will be like 50. Okay, the pressure, arterial pressure of our CO2, and what do we know from acidosis? The normal CO2 levels are 40. So 40. Now this R is our gas exchange ratio. Basically, it's R equals CO2 over O2. I'm pretty sure. Just making sure. Yeah, that's right. Okay, so R, that's right. R equals CO2 over O2. So it'll equal different amounts for different things, right? We produce CO2 when we metabolize. So when we metabolize glucose, it's 1. So I'll put R glucose. Why? Because the amount of CO2 to oxygen we produce is 1 to 1. R for fatty acids is about 0.7, meaning we produce about 3 carbon dioxides for every 4 oxygens that we produce. Or, I mean, we use 4 oxygens for every 3 carbon dioxides that we exhale. So, it's a little bit different, but for a normal, healthy human, it'll fall into 0.85. Now, say you're like diabetic and you can't metabolize sugar because you can't. It'll be closer to 0.7. For a normal, healthy human who's doing both types of metabolism, it's 0.85, somewhere in the middle. So that's what that usually is. So, we run the numbers. Here, this is like 47. This is like 710. This is 0.21. You run it all together, using PEMDAS and correct multiplication, you get 102 millimeters of mercury. And that is our partial pressure of oxygen in the artery. Just like this. Oxygen coming out into the artery. So yeah, that's how that works. I'll show you video. Okay. I have to check because I've left it and it hasn't videoed sometimes. Okay. All right. Now we're going to talk about oxygen and carbon dioxide exchange. So here's an alveolus. It's your capillary, right? Okay, so we have O2 in here. Partial pressure pressure of O2 equals 102 to about 104. Okay, and it wants to come into the blood. We'll diffuse into the blood, and it'll be about the same in the blood. Carbon dioxide is about 40, and so what will happen is we have a venous pressure here, venous artery. We have a venous, so PbCO2 equals 45. And so CO2 wants to go this way, right? But how do we carry CO2? How does CO2, most of it's not dissolved in the blood actually, believe it or not, only about 7% is dissolved in the blood. Well, what about the rest of the CO2? We'll talk about that in a sec. But here we go, right? We have our red blood cell here, and we have our hemoglobin. It'll bind 4 O2s per hemoglobin, about 250 million hemoglobins in a cell, so about a billion oxygen molecules per red blood cell. Yeah. So that's how that works there. So now this guy's gonna go throughout the body. And now when he goes throughout the body, I'm gonna draw it down here. So this goes down here. Here's a cell undergoing respiration, right? And that's building up CO2. There's like a lot of CO2 buildup in here. What will happen hemoglobin will come by. How does it know to release its O2? Well, CO2 will come out of this cell. It's nonpolar, so it diffuses freely across the membrane, and it will bind at this allosteric site on one of these hemoglobin units, subunits, and it will cause oxygen to come off. How does that work? Well, let's look at hemoglobin. I'm just going to bring this. And if we come over here, I'm going to draw a very crude. Hemoglobin has two states. It has a T state, tensed, and in its T state, it can't bind oxygen. Oxygen won't bind to it. However, here, if we look at the R state for relaxed, right? R, oxygen will bind just fine. And how does that work? Well, within hemoglobin itself, we have iron, right? Oxygen wants to bind to the iron, right? Oxygen wants to bind to the iron, and then we have a porphyrin ring around it. Well, in a tense state, what happens is the electron cloud of the porphyrin ring will actually cover up this iron so oxygen can't get through. So in the R state is when iron is exposed, and oxygen will bind to it just nicely. So basically, this is really cool how this works. So what happens is CO2 causes the hemoglobin to go into the R state, releasing O2, which the cell needs because it's metabolizing. Okay, and now carbon dioxide can be carried on hemoglobin here, rather than just dissolved in the blood. And about 23% of our carbon dioxide is dissolved in the blood like this. Okay, so now we come back, and, well, yeah, come back here. Let me just put my... So yeah, hemoglobin has this interesting way, and so that's kind of how that happens. Is carbon dioxide comes off, oxygen will come on as it goes back to the R state to allow oxygen to bind and go make another round. And about 23% of our carbon dioxide is bound to this hemoglobin. Okay, well, what else can red blood cells do to carbon dioxide? Red blood cells too, I'm going to draw it out here. They actually have carbonic anhydrase. So CO2 will come here and get converted to bicarb and then secreted or excreted to the blood. And about 70% of our CO2 is in the form of bicarb. So that's how we deal with CO2. O2 just rides on hemoglobin. So, another thing about red blood cells that I should mention here. So here's an RBC. Here's an RBC. They don't have mitochondria. So no mitochondria. Well, how do they respire? They do glycolysis, right? So red blood cells will take glucose, which is a 6-carbon chain, and they'll, through some steps, through glycolysis, right? I'm just gonna explain it, right? Glucose 6-phosphate to glucose 1,6-bisphosphate to fructose 2,6-bisphosphate, or I don't know. I forgot it already, but you know what I mean. You get pyruvate. You get 2 molecules of pyruvate right here. Sweet. Now, or, you know, we get, but an intermediate in there I should mention, sorry, is this 1,3-bisphosphoglycerate. Now there's an enzyme called 2,3-bisphosphoglycerate mutase. And what it does is it transfers that phosphate onto the second carbon here, and it makes a very unstable molecule. And what this does is this actually will go and it fits perfectly within hemoglobin in such a way that it causes it to release all of its oxygen. It causes it all to go into the T state. So oxygen will get released. Now this metabolite is actually excreted by cells as a way to get them to, it's present in red blood cells and it's present in placenta cells to get oxygen to release. So yeah, that's how that works. And then another thing that's important is protons also can bind to hemoglobin, right? They bind and they can cause oxygen to come off. So if you're acidic, if you're acidemic, that would cause your hemoglobin to lose affinity for oxygen. Another thing that can cause this as well, as I should mention, and why you get winded when you get feverish, is heat. Heat can actually trigger this as well. So we have a curve here for oxygen saturation, and yeah, we'll talk about that in a second.